1, 2, 3, 4, 5, 6, 7. Was everything so bad last time that the people started dropping course? Or did it scare someone with the title of today's meeting?
The title of today's meeting.
Okay, so it is not the case. Whom are we missing?
That and Jack.
Yes. Those two.
Should we email them?
I'm sure they'll show up.
Here's one of them.
Yeah,
Yes. Aha. Hi there. How are you? Good. Tough? Weak?
No, just experiments giving me results that make me a very unhappy individual.
Well, what can I tell? Compute them.
Oh, I have a feeling I know what it is. That's the problem.
Oh.
Is that some human error or?
Well, I'm hoping that's not the case, but that's what it's starting to suggest. So, I'm clearly doing something.
This is something that I was planning to give you like a month ago. It's like one more portion of thing.
One portion of thing.
Past this. So who we are and what are we doing?
We are students and we are learning.
We are what?
We are students and we are learning.
Learning. Yes, I would agree with this. We all learn something for the whole life.
Einstein said if you're not learning, you're dying.
You are staying on shoulders of giants. Who are not learning anymore. So technology was not so cooperative last time as one would wish. No? Better. So we are in the computational chemistry course. We do want to predict outcomes of measurements by running some software and some hardware, and we are accumulating theoretical background to know how it happens. By the way, the handout I handed out is in some sort answer key to one of the homeworks, where it requested the molecular Hamiltonian. And by now everyone is doing great with, if we would stop semester now, everyone would get A. Based on your excellent presentations and homeworks. So we are modeling molecules as a set of nuclei and electrons. We are writing Hamiltonian for them. We are writing molecular Hamiltonian, and then we split it on two parts with Born-Oppenheimer approximation. Then for nuclear part, we do limiting case quantum to classical transition, and we, for the rest of our life in the class, and we admit, agree that ions are point charges. So we neglect, at least it is not wasting. I'm not doing the duck sound. Until end of our life in the class, we consider nuclei as point charges, no quantum nuclear effects. And we went through the algorithm for for nuclear configuration optimization. bit of scratch paper. And then we stopped with anything about nuclear degrees of freedom. Meanwhile, each of you became a certified expert how to build atomic models. I hope you were not. Let me see here. You can watch yourself. So you do not accept positively what we did last time. Good. So now we are starting dealing with electronic degrees of freedom, and we already went one step forward by admitting Slater determinants, which drive me crazy. They drive me crazy for the rest of the life. I hate Slater determinants, but we cannot live without them. So the necessity to have the anti-symmetry requirements for electronic degrees of freedoms, the statistics for fermions, the Pauli principle of Bohr principles for atoms, all is connected with this Slater determinant. You are looking forward to 2 senseless lectures that you can just lean back and sleep. There will be completely no practical reasons for today and Thursday. It will be a little bit of intellectual advance, but more for completeness of your views. So we will not go too much forward. The big goal for about 3 weeks to go is to learn the simplest, I wouldn't say quickest in computation, but simplest in logic theory that helps to compute electronic structure of any molecule. The name is Hartree-Fock theory. So we will be dealing with it for about 6 meetings. The major challenge that we have discussed a week ago is what? We will not be wrong if you tell that major challenge is large number of degrees of freedom or large number of electrons. And the wave function depends on a lot of degrees of freedom, a lot of positions of electrons, or so this too heavy object for both analytical or numerical description in a blind, straightforward way. So we need to do tricks. And the main trick is to represent wave function that depends on many positions of electrons as a product or something like product of many one electron wave functions. Use atomic wave functions as building blocks to construct many electron wave function of a molecule. Whew. At least I remember where we are and what is our goal. And the Slater is a kind of bridge between atomic orbitals, hydrogen-like atom orbitals, and wave function of a molecule. Slater is the procedure, is a translating mechanism. Within these 6 meetings, about 3 weeks, we will look at the very simple idea which sounds as follows. If we have our favorite electron, and we are very interested in the intimate life of one electron, then we will learn that this, according to molecular Hamiltonian, the behavior of these properties contributed by this electron will depend both on where the ions are and where the rest of other electrons are. So the rest of electrons create an efficient field, additional potential that modifies the motion or eigenstates of our favorite electron. That's it. If you accept this idea, you're done with next 3 weeks. we will try to maybe bring a little bit of rigorosity and mathematical language and maybe also computational language, so then when we run codes, we deal with this idea in a good way. Okay. So the challenge, well, it's not a paradox, it's just technical challenge that we do not know which of the electrons is our favorite. It could be this one or this one. And we do not know which electrons can be considered as the source of background charge that create additional potential. So we need to design a procedure where we can blindly pick up one electron and move the rest into the background, or toss them, pick another, and move the rest in the background, and nothing will change in the procedure. So using properties of single electron as a source to form the background charge of the rest of electrons. If you do it in a rigorous way with account of discovery of John Slater, then we will be fine. And then we will change our mindset. Right now, if we are in chemistry and we read the abbreviation HF, we think of hydrogen fluoride. In 3 weeks, if you see abbreviation HF, you will translate it as Hartree-Fock. That's, I'm just giving you heads up what you are looking for. So this does make sense. And first 2 lectures will be senseless, last 4 lectures will be very important. So these 2 senseless lectures will be dealing with a little bit of background where the equation for Slater determinant comes from, and whether we can neglect or we cannot neglect the spin, and what is the spin. If you were in recently in some sort of quantum course, you have this information fresh in your heads, and it will be just a little refresher. If you didn't, I will speak a little bit so that you get common language and we do not fight for how to name one or another mathematical object. So I would be happy to live in the universe without spin from mathematical point of view, but I'm not sure if I can do it, if I'm allowed to. So we need to make an additional effort for this spin degree of freedom. Any objections? Good, very good. Practically, what are we going to do in the labs? We are going to compute electronic structure of the models that you have built. And there will be a couple of homeworks where you run the job, record one or another observable, and put it into whatever Word file, and then submit it electronically or as a printout. And we will go through several skills and protocols, procedures, how to do it quickly and efficiently with different pieces of software. So it is what we are looking to when we need tomorrow. So if your life is boring and you do not know what to do on the weekend, you can practice a little homework which will take you 5 minutes if you are not standing up and leaving the room. This is something very, very basic related to the specifics of speed degrees of freedom. Do not laugh if you understand how to do it, and do not panic if you don't. It's really simple, and you will be feeling very comfortable about this little assignment in less than an hour.
It's more 5.
No, I screw up the numbering. It's either 3 or 4.
You already have 4 homeworks?
Hmm?
You already have 4?
This is number 3.
3?
Yeah.
3 maybe.
Oh, wow.
You guys are doing good with homework.
I'm 792.
It may also give the name of different university and different year. Okay. In about 3 weeks, maybe not 2, it should be 3. We should make similar. Oh, let me put it in a different way. Originally, we agreed that we do not like exams. If suddenly you start loving exams, I do not mind to organizing them. But if you do not change your mind and we do the same as we did before, I suggest that we skip them and do just presentations, which will count as something really valuable and helpful. And if we have approval of this idea, you may develop an interest. What will be the subjects of presentations when we come to present next time? I will slightly modify and distribute. So this here is the tentative list, which consists of 8 points, and I will expand 8 to 10, so that there will be sufficient activity for each of you. But if you throw a glance on this printout, you will have an idea what are our goals when we meet for the lab. Okay. Now I can dim the lights. You take your popcorn and just watch the presentation. Content. Did I put it on the record? I don't remember. It's even challenge. Different button. Yes, good. So here. Last time it was writing, this time it does not. So at least I update. What? Good. So here is the number of our lecture. Here is the more or less correct number of our course, and we are setting up a goal to be proficient in Hartree-Fock, and of course we will run the electronic structure of the models with this method. We can do it without understanding anything about the method, but we will feel, I hope that we will feel better just understanding what is going on. So this is the little assignment that will be super easy in shortly, and here just overview what we will be practically doing when we meet tomorrow. So we will browse between directories that you have probably already created for different models and run jobs, so that when the jobs are complete, you can analyze them and collect some data. And a little overview, so that there will be two different ways to analyze results of computation. One is to use pop-up graphical user interface, when you use Gauss view to analyze output of your computation and click just show me results, and then it underlines whatever you need with primary goal is total energy. And another one is to go through the text output files, which is a little more boring but more reliable, because graphical information is not as quick and reliable as text information. So if you do just a couple of models per life, then we do not need any text. We do everything in GUI. If you are doing 1,000 jobs, we cannot live without text. We will need to analyze text type of output. So here is the list that we'll do in about 3 weeks. And the best stuff, if you would make, we'll do again the democratic procedure of voting, collecting your opinions. If I would need to present, I would choose plotting molecular orbitals, because it's mostly spectacular. So it is a sweet spot on my point of view. So here is a very brief summary of what we did a week ago. So we dropped anything related to nuclear degrees of freedom, left only kinetic energy of electrons, interaction with nailed down ions and electron-electron interaction, and the big function, many electron function of the all electrons can be composed of one electron atomic orbitals residing on all ions in the molecule with help of Slater procedure that looks like a determinant. But so you count orbitals in one direction and you count electrons into another direction, and then just blindly follow the rigorous procedure for computing determinants, which shouldn't be very surprising for you, right? Give me a little secret sign if you never heard the word determinant before. No? Okay, so it is a way to consolidate many numbers in matrix into one number by a specific procedure, by adding and multiplying several elements of matrix in a specific order. One can construct one number, and this determinant is so important because depending on the numerical value of this determinant, a mathematician can say whether it is a good or bad matrix. Specifically, it is interesting for any mathematician whether the determinant is equal to 0 or not. So some matrices give determinant equal to 0, some not. So just a little recall of linear algebra. But we are using this procedure to match anti-symmetry requirement of many electron wave function. What did we learn in modern physics or in freshman quantum theory, if you had such? No, atomic chemistry section of the chemistry 101. We probably have learned there that in hydrogen atom there are eigenstates, and they are counted with 4 counters: principal, angular, magnetic, and spin. Right? So here they are: principal, orbital, magnetic, and spin. Okay, my memory serves me well. So we should be more or less happy with first 3, and the spin is counterintuitive. At least for now, for us it is okay, but like hundreds of years ago it was intellectual challenge to accept this concept at all. And if I mute the microphone, but the formal definition of a spin is an additional degree of freedom that can have only two values. And it is measured in the units of angular momentum, although it is not really angular momentum. It's internal degree of freedom. What is here?
That's alpha.
No, not specific symbol, but generally what it is.
And you initiate. Wow, I cannot. You're creating something, acting on it.
So it is some abstract mathematical expressions in direct notations. So what right now we are not going to look into depth of actual physical processes. We are like I have no idea what accountants are doing or bookkeepers, but my humble understanding is they don't care where money are coming from and where they're going to. They just care about how to categorize them in right folders. Right now we are doing the same with spin and other quantum processes. So we need to have the language to follow what is happening. So if there is a quantum degree of freedom, and it can be in different states, we need to have a language to tell about it. If the state of this quantum system is changed due to some unknown reasons, we need to have an object that will control this conversion. And we should not we should accept, agree, and all of us should use the same notation so that we understand each other with happiness. So spin degree of freedom has two values, which can be noted as thumb up or thumb down, plus or minus, alpha or beta. What else? Arrow up, arrow down. And Dirac got his scientific awards because he suggested to use angular brackets. He suggested that it will resolve several ambiguities in notations because it allows to treat more in a more general way both wave functions that have infinite number of degrees of freedom and vectors that have finite degrees of freedom, or spin that has only two values for spin degree of freedom. So broader range of concepts can be used with, can be described with this direct notation. Okay. No, this is boring. Here is the true science. Consider an O. I don't know, in different countries there are different colloquial language, but in some there is a, people call a person who wakes up later all and who wakes up earlier as skylark. Or maybe there are different words. Is there a specific word for someone who gets up early?
Early bird.
Early bird, okay, good. I've heard only about early bird breakfast or early bird check-in to the airplane. So suppose we have an owl. Suppose we have a wizard that tells hocus pocus and converts an owl into an early bird. Okay? So it is the level of intellectual advance how I like to discuss quantum theory. Now, we do not look into mechanism, how the owl was converted into early bird, but we need an accounting, quantum accountants, how to count what is going on. So what does it mean to convert an owl into early bird? So here we get the contribution from Paul Dirac. So instead of just drawing all and early bird, he tells, no, it is important to draw angular brackets. If you draw angular brackets, everything will become more mathematical and more rigorous. So Dirac notations means angular brackets. And now we make it as an equation. So if wizard acts on cat vector, Dirac vector of an O, one obtains the early bird. Good? No objections. Now, comparison. Like, if we have an all, but we didn't name it yet. If you have a random bird, we need to tell who it is. And we go into director and compare, like, this face to this face. Is it a tiger? No. Is it a cat? No. Oh, it looks like a O. And then comparison gives positive, 1. So doing different directions of angular brackets, and we see that all compared with all is positive, 1. Or early bird compared with early bird gives also 1. But if you compare two different objects, negative. All is not the same as early bird. Or as we see later, spin up is not the same as spin down. Good? So fancy word is scalar product in Dirac space for this comparison. Now, see here the angles go a little different way. This is the way to convert one object into another one. And the conversion, the fancy word is dyadic product, works the following way. So if we have different objects on the left and the right, we can apply this conversion object to our O. Right? So this dyadic product is applied to our wave function. No objections. Now we think outside of the box. We keep the same construction, but we change our angle. So we focus on these two objects together and this separate. Now it is comparison of an O to an O, which will be 1. And algebraically, mathematically, this converts into 1 and disappears. And then mathematically we get an early bird. So we do have an abstract mathematical tool that takes into account conversion of one quantum object into another one and allows comparison, and we are becoming certified experts in Dirac notation. Some of you were such experts long before. Let me scroll to a boring slide that I was showing before we went to birds. Okay. So now we can set up the analogy between birds and spin states. So if we have two spins that we want to compare, we can call them alpha and beta, and it can be either 1 or 0. And if you want to convert one spin into another, neglecting, forgetting how, we just do this dyadic Dirac product and put one spin here, another there. And we can also give names for it. If we convert from down to up, we can call it, okay, plus, raising operator. If we convert from up to down, we will put minus here. Okay? So same thing as with birds. So here this alpha is our owl, and this alpha beta dyadic product operator is our wizard. So we change our angle and consider it as comparing this alpha with alpha, which gives 1, and therefore we obtain beta. So by acting on by this S plus onto alpha, we are getting beta. I think it's one of the lines in your homework, right? Is it there? You can immediately scratch it to save your time in the future. Same thing with minus. Then we swap the order. We have beta on the left and alpha on the right. And if we apply this S minus to alpha, we change our angle and look on the last two objects. So beta compared with alpha, beta is not the alpha, therefore it will give 0. And 0 multiplied algebraically on anything will be 0. So if we, this is an interesting property, that if you try to flip down, the spin is already oriented down, we get 0. It is not possible. So through these mathematical tricks, one can get some silly on the first glance, but very helpful for precise accounting and rigorous tracking of the properties of spin degrees of freedom. Not tired yet? Not bored yet? So, the one little thing about quantum world that is different from everyday experience and classical mechanics, that you have already accepted this idea, and we were using it many times. So that wave function generally can be represented as superposition of several basis functions, right? Which means that it can coexist in several states at the same time. So here we do have spin state. This sigma is composed as superposition of spin up and spin down with some coefficients, with some weight coefficients, probability amplitudes. It means that it can be up, it can be down, or it can be at some arbitrary angle. And by applying the operators, this raising lowering operators, to general spin state, one can learn a little bit more. How many percent, how much is the probability that it is up, or how much the probability that it is down. So if we build an operator that is plus times minus, so it will be converting up to down, not converting down to up. Too many symbols. We can merge them together, because alpha times alpha will be 1, and we'll flip it away, and then it will be beta times beta. So this is a projector operator. So if the quantum spin was in state beta, it will repeat itself. It will change nothing. If it was in state alpha, it will give 0. If it was somewhere in between, it will give percentage. How much is probability that the state was in the state beta? Projector operator. projector operator. So how do we practically, well, nothing practical, all abstract and imaginary, and it is a little far from our major goal of doing computations. We're just acquiring a little bit of language. So if we want to construct a mathematical procedure to get the probability that the spin is in state beta, we cannot just apply operator to the wave function. We need to make so-called convolutional matrix element where we have the same quantum state in its bra and cat form. So, and if we swap the direction of angle, we also need to put star complex conjugate in front of these coefficients. And then we do such construction. The operator of our interest, bra conjugated on the left, cat on the right. So this will give the number, the answer to expectation value of our operator. So if you do this procedure for this general spin state and do it carefully, we will get the same answer as we intuitively knew based on the definition of this quantum amplitudes. So C beta stars times C beta. Probability that it is in the state beta. Objections? Discomfort? No? Bra, operator, cat. Let me exercise this thing on the blackboard, otherwise I feel it can get a little boring. So this is projector operator, this is bra, and this is cat implementation of the quantum state. So there are two terms here, two terms there, so the total number of terms will be 2 times 2 will be 4, right? C star, C alpha, beta, beta, alpha. This, and this. So now we are looking on comparison. Comparing beta and alpha are different. They do not coincide. 0. Alpha and beta are different. 0. So the whole term is gone. Beta times alpha are 0. So the whole term is gone. So if at least one term is 0, we don't care about others. Here, this one is equal 1. This one is equal 1. So this is only surviving term. So it will be P probability that spin is in the state beta is C star beta times C beta. So this is kind of intuitive answer, but if you have something a little more complicated, then intuitive thinking may fail. And this gives a protocol that one can repeat again and again, or use in some derivations of equations that later are programmed for quantum chemical calculations. So here is the same thing. 4 terms, operator in between. And for each term, we can put coefficients on one side and this combinations of Dirac notations on other. And we look through all of them. It will be zeros, 0, 0, 0, and only the last one is non-zero. That gives the answer. Another thing that will bring us to the origin of Slater equation is connection between this abstract objects for flipping spin, raising operators, spin up, spin down, and actual projections. So if you know from your background about electronic paramagnetic resonance or nuclear magnetic resonance, if a material does have non-zero spin of one or another origin, it will respond to magnetic field. It will show some magnetization. And magnetization can be measured in different directions. In a silly way, one can approach a piece of material with compass and see how will it respond to it. So there are 3 projections of a material with non-zero spin, 3 projections of magnetization, and the spin operators are related to these projections. So if one does corresponding appropriate well-defined combinations of these S plus and S minus operators, one gets projections for Sx, X, Y, and Z projections of magnetic momentum originating from spin. And the combinations for X and Y are here. And for Z, it is also not very complicated. So a little summary of how we were wasting our time today. We got several concepts that we can address verbally by Dirac notation or in matrix notation that we didn't cover, but it is still possible. So we have the Bra and Ket Dirac notations, which means angle left or right. We get a concept of superposition, which can be also Bra and Ket, and we get raising and lowering operators that flip up and down. And if someone is curious, right now we do not need it, but it can be also translated into 2-dimensional vectors and matrices. We will be earlier today. So here is the plan. How we are wasting our time today and on Thursday, and then we'll do something really useful, helpful, and serious, in addition to most important practical labs on Wednesday nights. So Slater determinant is the key, or the goal is Hartree-Fock theory. The starting point is Slater determinant. we are wasting time to justify where it comes from. I don't know how about you, I was angry on Slater for all my conscious life, starting from time I heard about it for the first time. Maybe you are more friendly to this person. So I always wanted to see a justification, not just the equation. Then we will go through the concept of mean field, which means all but one electrons create background charge that affects on our favorite electron. Then we cover the concept of correlation and exchange. So in addition to attraction or repulsion between electrons, there is an additional contribution to many electron energy system of energy of many electron system that originates from hypothetical opportunity for two favored electrons being swapped. If one considers into account a possibility of their exchange, it brings an additional term into the energy. If one doesn't take it into account, one gets in trouble. Very far from experimental results. And then, as the top achievement of our 3-week, 6 meetings session, we will draw a flowchart how Hartree-Fock theory is working and why it gives more or less precise data. Here's the plan. We will have test materials. I congratulate you with what? I congratulate you with the fact that we have finished several minutes earlier. I announce lecture number 10 complete. And I will stay here in case some of you have questions or any discussion points. Done. Meeting is dismissed.